Hello everybody, welcome back to Algebra 2, and my name doesn't matter. So, what we're going to be talking about today is complex numbers. So, complex numbers are a weird thing, that's what we're talking about. So, what's a complex number? Well, first, to talk about complex numbers, we need to talk about imaginary numbers. So, remember that the square root of 9 is 3, but the square root of -9 is unknown. It's not -3 because -3 squared is 9, but this notation indicates only the positive root. So when we get to a lot of things later on, we usually see something like some ugly thing, and we don't know how to evaluate this, but we can evaluate it if it's positive. So what we do is we know that the square root of a times the square root of b is equal to the square root of ab. So let's say b is 4/3 over 7 x to the y, right? Then if we want the square root of -4/3 over 7 x to the y, then we're multiplying by -1. So a is -1. So that is the square root of -1. And we always do like this. If we always have something with like a negative square root, we always break it down into the square root of -1 and it's positive. Now square root of -1, we don't know that. And we want to keep writing square root of -1 over and over. So we say that's equal to I. So I'm going to keep that up here. I is equal to the square root of -1. Or I squared equals -1. Now, of course, I is like, yeah, we know that now, but what about I cubed and I to the 0th, I to the -1st? So now we know that I to the 0th equals 1. What about I to the 1st? Equals I to the 2nd, a squared is -1 by definition. What's I cubed? Well, I cubed is I squared times I. So that's -1 times I, or -I. Now what's I to the 4th? That's I squared times I squared, and that's -1 times -1, or 1. That means that I to the 5th is I to the 4th times I, which is I. And then we notice now it's going to repeat. And then that means it'll repeat in the opposite direction too. So I to the -1st is -I. I to the -2nd is -1. I to the -3rd is I. So so now that we know the powers of I, we can get into more complicated things. So we know what I is, the powers of I. Now we're going to talk about complex numbers. So these are imaginary numbers. 3i, 7i, I over 2, I plus, no, sorry, yeah. If we multiply I by anything or divide it by anything, it's an imaginary number, which means that it's not on the number line. But what if we were to combine them? What if we had I plus 2, or 3i minus 4, or I over 2 minus 7? If we have an imaginary part and then we add a real part, it's a complex number. So real numbers are, you know those, right? It's like -2, 7, 0, square root of 2, pi, e, everything. Now, we talked about I, right? So let's say, complex numbers are in the form of this. God, so complex numbers are in the form a plus bi, where b can be positive or negative and a can be positive or negative. So like 3 plus 4i, 7 minus 2, 6i, 2 minus 4i, so on. So a is the real part, which is indicated by 2 lines and then like an R. And then we also have the imaginary part. So there's going to be an I and this, and B is a real number. But BI is an imaginary number. Like, so BI is never going to be on the complex plane. But A is, BI is never going to be on the number line, but A is. So now that we know the form of a complex number, we can look into it more. So what if we had, so we usually like we have like x is usually unknown, y is usually an unknown, z is usually an unknown, a, b, and c are usually constants, right? N is usually arbitrary number. We have all those like usual variables. So for complex numbers, we use z. Okay. Now some notation for z is z with a line over it, and that means a minus bi. And then you might wonder why that's the case, and we're going to look at that in a bit. And then if you had we're actually going to be looking at this right now. So what does z with a line over it mean? That means the conjugate of z. So the conjugate of anything is just when you're adding two things and then you flip the sign. Okay, that's basically what a conjugate is. So what does the conjugate z and z have in common? Well, I said, remember when we were talking about special factorizations, that a squared plus b squared cannot be factored, but a cubed plus b cubed can. So if we had a squared plus b squared, well, what could we do with that? We could say that that's a squared minus negative b squared, right? If we had that, that's going to be equal to a squared. That's going to be equal to using our difference of squares formula. We're going to get a and now plus the square root of negative b squared times a minus the square root of negative b squared. Maybe if you notice this, you might have done that and you might have got stuck here when you saw the negative b squared. So what do we do? Well, now we know how to separate it, right? That's equal to a plus bi, right? Because we can separate that into the square root of negative 1 times the square root of b squared. The square root of b squared is b, and then the square root of negative 1 is I, so bi. Same thing here, we get a minus bi. And now we notice, this is, let's say a plus bi is z. then this is over here is just the conjugate of z, right? We flip the plus and minus. So now we know that z times the conjugate of z equals a squared plus b squared. It's not a factorization because we can't really use that because this is it's imaginary and complex. Okay. So now we're going to talk about what happens when we do some things with it. So what if we had something like, what is 4 plus 3i divided by 7 minus 4i? This is kind of like rationalizing the denominator, but instead of rationalizing it, we're just making it real. So how can we make the denominator a real number? Well, we can multiply by 7 plus 4i, right? Because now we know that if z is complex, right, a plus bi, and then we multiply by its conjugate, which is also complex, we're going to get a real number, a squared plus b squared. So we want to make this bottom a real number. So we multiply by its conjugate. So 7 plus 4i over 7 plus 4i. Now the top, we have our binomial. We have a binomial times a binomial, or we can use FOIL for that. The bottom, that's just 7 squared minus 4i squared, which is 49, minus 16i squared. But because I squared is -1, we flip the sign and we get plus 16. You can also know that z times the conjugate of z is just the sum of the squares. So it's 7 squared plus 4 squared. We expand the top and we get 28 plus 16i plus 21i minus 12, because I squared is -1. So a good tactic is just to act like I is a variable, like x, okay, like we're just expanding it, ignoring it as a variable, and then if you see an I squared or an I cubed, then we simplify it. Over 49 plus 16, that's 65, I think. Yeah, 65, good. So now the top we can simplify even more, and that becomes sorry, I can't think, 16 plus 37i over 65, and that's our answer. But we like to write it in the complex notation, which is 16 over 65 plus 37 over 65i, like that. So now we know how to divide them, and while we were doing that, we also learned how to multiply them, right? We just act like it's a variable, like x, and then we just expand it all out. We also learned over here how to add and subtract. So what we did was we just combine. So again, we just act like it's a variable x, and we combine like terms. What terms have an I in it? What terms have what terms don't have an I in it? Because now that we know that they can only be in the form real or imaginary. So imaginary will have an I, real will have 1, I guess. And then I is if you had I squared, that becomes -1. If you had I cubed, that becomes -I. So we're going to have either I or 1 as our unit, and that'll make more sense in a bit. So we learned how to do all the operations with complex numbers. Now we're going to talk about, so we talked about what it is, adding, dividing, multiplying. Talked about that. Now I want to introduce to you something called the complex plane. So how do we graph these now, right? You might be wondering, how do we graph these complex numbers? So, oops. It's really laggy. Yeah, so how do we graph them? Because when we have our normal axes, they're 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5, right? So negative 1, 2, 3, 4, 5, right? So we can't really graph I on that. But what we can do is we can create a new type of coordinate grid, or new type of Cartesian plane, which is called the complex plane. The complex plane is where we can graph anything. So now it's like expanding our ideas of 2D into 3D kind of. So on this we have a number line. So 1, 2, 3, 4, 5, 6, dot dot dot. On this side we have -1, -2, -3, -4, -5, -6, -7. Now instead of having 1, 2, and the same thing on the vertical axis, we're gonna write it like this. So the unit of, so we know that the unit of real numbers is 1, but the unit of imaginary numbers is I, 2I, 3I, 4I, 5I, 6I, 7I. Now notice these are just the square root of -1, square root of -2, square root of -3, square root of -4. So this isn't really creating a square. This is really creating a rectangle. If we wanted this, like, this is not like this would be square root of 1, square root of 4, square root of 9, like that. So we'd have to make it 1i, 4i, 9i if we want it to be the same scale. On this side we're gonna have -I, -2i, -3i, -4i, -5i, -6i, -7i. So now if we were to graph what's 4 plus 3i, we look at this real part, and actually we might as well just label these. But now we can't do x and y. This is the real axis, the real numbers, right? And this is the imaginary axis, or the imaginary numbers. So we graph the real part, 4, right here, and then we do plus 3i. So 4 plus 3i just becomes 4, 3 in the real plane, or in the Cartesian plane. So a plus bi becomes a comma b. So we have 4, 3. So if we go 4, then the imaginary part's 3, so we go up 3. So to here, 3i. Now, what is the graph of, and now you know why we don't use I, 4i, 9i, because now it makes more sense, right? Because a comma b and a plus bi. So now how would you graph -7 minus 2i squared plus I? Well, this -2i squared becomes plus 2, and this becomes -5 plus I. So we get -5 plus I. So now we know how to plot the points, right? You can use your basic knowledge of the Cartesian plane to know the rest. So now I'm gonna begin talking about a little bit about like some more some more things about the Cartesian or the complex plane. So now, how would you graph maybe a circle in this plane? A little harder, but we know how to graph circles and ellipses. We learned that in the last video, but now we need to do it in the complex plane. So first I'm going to show how to graph a line, but before that I want to talk about more notation. So bar, z, bar. We could also use 2 bars, but we actually use 2 bars later on. So this is actually notation of absolute value. If you don't know what absolute value is, if you're at the absolute value of a, where a is a real number, right, from negative infinity to infinity, then that's just equal to the positive version of it. So if it's negative, then it'll become negative a. Then if it's positive, it just becomes a. And it just becomes 0 if 0. Now, we're actually going to learn about these kind of equations later on. They're called piecewise equations. You can actually see them right here. So, piecewise equations are just like if it's under these circumstances, then it's a different thing. But if it's under these circumstances, you do this instead. So, so an example is like you just make it positive. So if you had the absolute value of negative 3.7225, that's just 3.725. If you have the absolute value of 7, that's equal to 7. It's basically the distance of that number to 0 or from 0 on the number line. So now when we have the complex number, how do we know, like now we can extend that idea of absolute value to the complex numbers. So what does absolute value mean in the complex world? So instead of distance from 0, it's distance from 0, 0, or the origin. Because 0 is 0 plus 0i, right? So it's still the origin. Now let's say we at some point, let's say 4 plus 3i. This is z. What is the absolute value of z, or the magnitude? That's what we call it, the magnitude of z. It's just the distance, so it's like that. How do we find that? Well, we can use our distance formula or Pythagorean theorem to create a triangle. Either way, right? And we know that if this is a plus bi, then this is b and this is a. So this is the square root of a squared plus b squared. So now we know what the magnitude of z is. Okay. Yeah, so now if we wanted to graph a circle, instead of the distance from the center to that point, we're going to find this. So first, if we want to find hold on, let me draw this graph back. Good enough. You know what? Hold on. Okay, so Yeah, so now we can rewrite this. So now, if you had some point, let's say it's a center. So let's say it's 2 plus I. That's the center of our circle. And now let's say we had the radius of 2, right? The radius can't be negative. Good enough. So now this is our radius. What's the equation of the circle in the complex plane? Because if you were to graph anything in the Cartesian plane and then graph it back in the complex plane, it'd just be a line. So yeah, it'd just be squashed down. So now, how do we do this? So let's say we had the center of, again, h plus ki, or h comma k. Then we have now we're looking for all the points z, which is a plus bi, such that um the such that yeah, so we're looking for all the points such that the distance from h plus ki to a plus bi is r. Now we can use distance formula, but in a different way. So we're looking for all the points, right? So we just have, if this is a plus bi, right? This is just a minus h. This is b minus k. So we do those squared. So r is going to be equal to the square root of a minus h squared plus this is b minus ki, right? So plus b minus ki squared. So that gets us to r squared is equal to a minus h squared plus b minus, or not plus, minus b minus k squared. Kind of like the same thing, but it's a minus instead. I think that should be it. Yeah, so yeah, okay. Wait, no. Yeah, okay, that's b minus k, and then because we're graphing it, we want to use x and y. Now we can also actually simplify this even more. We can say that r squared equals x minus h whole squared. Oh, sorry, no. Sorry. It's really laggy. Okay, so this isn't really coordinating well. So this is x, this is y. We can actually simplify this too. Okay, we can simplify this to r squared equals, and now you can use difference of squares. So we have x minus h minus y minus k. So we have x minus y minus h plus k, I guess, times x minus h plus y minus k. Or let me write this as x plus y minus h minus k. Alright, now yeah, that should be it. If I'm wrong, I'll correct myself in the next video. But thanks for watching, and I'll see you guys next time. Goodbye.